This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
With that, let's get started in advanced post-processing in ANSYS Mechanical. After performing the best analysis to simulate your part's particular performance and the various analyses you may need to perform, it's important to communicate those results effectively. So today, this webinar is going to focus on advanced post-processing methods. There are a number of existing post-processing techniques. We're going to focus on a few of the advanced topics and some of the new topics within ANSYS version 14.5. So I'd like to demonstrate solution combinations today, also user-defined results objects using construction geometry with path and surface plots, and then combining various results quantities and displays through chart data. Also, we'll cover some of the force and reaction probes and see how those can be utilized for various results. And then we will be demonstrating accessing and plotting node and element results directly in Mechanical. Also, if some of you have some MAPDL commands that you use for post-processing, we'll show you how to use those within the Workbench environment and access and pass back and forth some key information data. The particular model I'll be covering is a structural example. This is a pillow block tied down with a couple bolts with some bolt preload and some two various load cases. One, we have a bearing load inside this bearing race, and then also a secondary load where we apply a pressure on this face. This particular example is a structural example, but I know that you may have other analysis requirements. Some of the post-processing techniques we'll show you how to do is very applicable to those other analysis. So let's go into Mechanical directly. And first thing I'd like to show you is solution combinations. So in my outline tree within Mechanical, I have a couple static structural analysis with two design conditions. So I've got design condition 1 and 2. Both of these are structural analyses. I'd like to show you solution combination. When I'm going to talk about a number of different items in the outline tree, if you highlight the model option here, this brings some other categories to put in or folders to put in the outline tree that may not automatically be there. The first one being a solution combination, because this combination can span multiple analyses types. Just to take a peek at our project page, in this example, I've got my geometry tied in to a static structural when I'm sharing the geometry, material data, and a model with another analysis. And this creates a multiple folder scenario. Perhaps we need to combine results for certain analysis quantities we're interested in. We can do that through solution combination. Once we add this item to the outline tree, we can come over to the worksheet mode, and if we right-click, we can start adding various combinations of everything in the outline tree. In this case, we specify a multiplying coefficient. We use the pull-down menu to select one of the environment names, and we can use this kind of spreadsheet to add a multiplying factor. For example, let's say we need 2.5 times this second design condition, and perhaps we want to combine results with this factor with this baseline design condition. Once we do that, once this solution combination is in the outline tree, we can then insert results just as if we were inserting standard results for the individual analyses. So here you can see we've got equivalent stress, maximum principal stress, some contact results, all our standard post-processing we can then now look at inserting new ones to combine those effects. So this solution combination, perhaps we want to say, I need the maximum principal stress, and for a factor of 1 times the design condition 2 plus 2.5 times the second design condition. I'm going to rename this solution combination to be, let's say, a maximum condition, and I'm going to look at our maximum principal stress. You can use the same kind of copy and paste as you do in the outline tree. If I wanted to duplicate this solution combination, I can then, let me rename this one. Maybe I need a max and a min for perhaps a fatigue analysis. Let me rename this min solution combination, and then I'm going to adjust this factor. Perhaps I've got a negative coefficient on the second environment. So now we can go back and evaluate the results for these two conditions, just as we would do for our normal. It goes and accesses the data and performs those calculations. And so if we have equivalent, if we have a maximum principal stress on our block, we can see we're in this range here. We take a look at these combinations. We see the increases for the maximum and the decrease for a min, and we can start perhaps building a load profile for a fatigue scenario. That's one tool here, and that's solution combination. The next thing I'd like to describe is user-defined results objects. So in our first static structural block assembly condition, we've got various results quantities, total deformation, equivalent stress. When we want to access results that are stored in the binary results file, RST results file, we can take this solution folder and come up to the worksheet. You'll also see in the solution folder we can insert a user-defined result. One of the handy ways to access user-defined results is highlighting the worksheet and look at all the available results quantities that you may want to plot in Workbench Mechanical. So you can see various results quantities that may not initially be available via the pull-down menu. You can kind of pick and choose which quantities you need, and the key thing is to utilize the expression in developing a user-defined result. So, for example, if we decided, just as a comparison, if we wanted this user-defined results as the resultant displacement, we can right-click, create a user-defined result in our outline tree, and evaluate that right away. That'll one of the key things with user-defined results in the details pane is looking at the expression, and then I'll show you an example with identifier. In this case, USUM is just the root sum squared of the displacements, and that should match our total deformation. You can see the numbers don't change. We're just accessing the results file directly. Let's say we wanted to add another user-defined result, but we wanted to define the expression of results quantities ourselves. Just as an example, you can use mathematical functions and access the individual identifiers directly. So I'm going to type in a square root function and sum up ux squared plus uy squared plus uz, and just do the calculation on my own just as a test case to start working with expressions. And once you enter that, click that, it just shows up with the yellow lightning bolt. You evaluate that just as you would another results. In this case, this should look exactly the same as USUM, but then once we've kind of tested our expressions, we can start working with and extracting data that we may want to do calculations ourselves. Another example with user-defined results is you may want to perform some type of expression with previous user-defined results. So let's say for this USUM here, we wanted to evaluate this instead of at the last time period, I've got 3 load steps in this analysis. I cinch down one bolt in the first load step, cinch down in the other, and in the last load step, I apply my bearing load. Let's say we want to look at the deflections at time 2, and I'm going to create this identifier, and this identifier will be called my block. With this identifier, once we evaluate the results, we can then use the identifier named my block. Here's our resultant. If I include another user-defined results, in the expression, I can say from the third load step, I could take the USUM the deflection at the third load step and subtract my block. So for example, if we wanted to look at a relative movement calculation from one load step to another, we can actually create that expression within the user-defined results, and then we can evaluate that. So this is just an example with displacements, but you could see you can perform kind of many types of manipulations with utilizing user-defined results and the identifiers amongst these. So this is kind of shows the relative deflection from load step 3 to from load step 2. And so just a small amount of deflection with locking down those bolts. So that's user-defined results. Next thing I want to show is the ability to do path and surface plots. With path and surface plots, these types of results plotting operate on construction geometry. Some of you may be familiar with ANSYS Mechanical APDL and using path and surface plots. The way to do it in mechanical is define some construction geometry and then scope your results to that construction geometry. So here we have a path, we have a surface. Let's define a surface where we want to take a slice through our model and look at some resultant stress on that. Maybe we need to do a force balance as well. So with this surface, they works on the XY plane of a coordinate system you define. And so let's go ahead and define a coordinate system real quick. I'm going to select this surface, define a new coordinate system. If I want to get a section cut through here, an arbitrary section cut through here, I'm going to take this coordinate system, I'm going to rotate it 90 degrees. That way I get the XY plane. And maybe I need to offset that Z position a little bit off the surface. So let's offset that 0.1 inches. Once we offset that, you can see it's kind of where I want to take that section cut. I'm going to rename my coordinate system cut. And then with this surface, come down to the details, and we identify which coordinate system we define. So I've got a coordinate system cut, and this will take a slice through my model. Once we've got the surface defined, we can also do that with a path, essentially do a linear cut through the model. With this surface, we can take a resultant quantity. Let's take a look at our first load condition. We'll insert a stress, let's say maximum principal stress. And with this, we can scope, instead of scoping to individual bodies like we do normally, let's take this maximum principal stress and scope it to, instead of the geometry selection, let's go down to a surface. Once we do that, it's nice because you have a pull-down menu for that previously defined surface. That's literally all you have to do. You can scope it, again, to specific bodies if you like. So let's go take a look at a section cut through this bracket. And once we've defined that surface, we can evaluate that results. It'll go in and take that, map that, interpolate those stresses onto your surface. So that allows you to map. There's that kind of, with pulling on this bearing, you can kind of see the bending, the principal stress in bending. Okay. With this, with scoping to a surface, you can also use the surface as a key component to looking at reaction probes. So let's take a look. Because I've defined the surface already, I'd like to show you another results quantity that's sometimes helpful. And let's go to Solution. And on the Probe menu, there's a number of probes that we use regularly. In this case, let's use a force reaction probe. This force reaction probe is typically scoped to a fixed support. It's one of the supports in your model to identify the load balance at a fixed condition, boundary condition. So instead of a boundary condition, we can actually scope this to an existing surface. So for the force reaction, I'll do a net balance on the surface you've defined, and you can just use the pull-down menu for that surface. And then you identify what parts of geometry do you want to use to add or to interpolate this to calculate that resultant force. And we can do this with moments as well. So with this force reaction, let's identify just this bracket as a way to sum up the forces and calculate the resultant force on this surface. So let's go ahead and insert those results. Let me go ahead, let me zoom up here, highlight just this. Let me hide all the other bodies so we can take a look at this results a little bit easier. There's our force reactions. So we can see all the little arrows, these directional arrows here for our equivalent stress. We can kind of see the bending moment through the section cut here. Sometimes this is a little difficult to see. This is pretty a good visualization. Sometimes we want to switch over to wireframe to look at how we're doing through all the nodes. You can switch to wireframe mode as well. We can also do this force reaction is against the section cut. You can also do this with a moment reaction probe as well. At this point, I want to just take a pause and get a little feedback from you folks. I'm going to open up a poll to kind of find out what kind of post-processing you folks do. Let me open up a poll. In this poll, we're going to ask, what type of FE post-processing do you typically perform? Are you just using mechanical to produce standard contour plots, or do you take all the data you're generating and export that to Workbench? Export that results to Excel or perhaps some in-house calculations? Or do you do most of your post-processing in only mechanical APDL? Or is it a combination of the bunch? So with these questions, why don't you take a moment to submit your answers? Here we go. Let me show the results here. Looks like a number of folks use a combination of many of the post-processing techniques. Workbench mechanical standard contour plots, and then a combination of mechanical APDL, perhaps some other data. Thank you for participating in our poll. Okay, the next thing I'd like to describe is continuing along the lines of force and reaction probes. Let me switch back to our model here. Let me show all of our bodies. Sometimes when we're working with some complex parts and we have bolt pretension and contact set up, we want to understand the loading throughout the model. We want to look at the load transfer through the parts. The next thing I want to describe in solution probes is, again, force reaction probe. We showed you scoping force reaction of boundary conditions and surfaces. Next thing I'd like to just show is you can also highlight or perform a force summation about a contact region. When you specify a contact region, it does allow you to use the pull-down menu from the contact you've set up. So in this case, I've set up a contact between the surface of the pillow block and my bracket. So let me just get rid of some of the other parts here. Let me hide the other bodies. When we set up the force reaction against the contact pair, it identifies, change the view there. It identifies the forces throughout your time history transferred through that contact pair. So sometimes that's helpful. In this case, we can see with load step 1, I have 400 pounds pretensioning one bolt, and I have another 400 pounds pretensioning at the time step 2. So here you can see the resultant pretension coming through this contact pair, and then as we load the bearing, you can see the various loads through this load transfer through this contact pair. Another way to monitor loading is specifically for bolt pretension is through a bolt pretension probe. This allows you to pick a specific bolt pretension. When you evaluate those results, this will give you a load history throughout the various time points you're performing the analysis. In this case, we're loading this up in load step 1. It stays locked in load step 2, and then as we apply load, the bolt pretension reaction is essentially the net sum of all loads acting through the bolt. So that would be the bolt pretension plus applied loads from the analysis. Right. The next thing I'd like to do in some of the new version 14.5 capabilities is show you results, capabilities of looking at just node and element, accessing those types of results. You can do this directly within a specific static structural example here by inserting a results quantity. Let's say when we want to look at a key component or results in a local area, we may want to not scope it to a surface or a body. We just want more of a local area. So let's scope equivalent von Mises stress results to only certain nodes and elements in the model. To do this, once we've highlighted the area we want to focus in, we switch over to Show Mesh. This shows the mesh on on the model, but then allows us to switch over to selecting mesh to scope this to this results quantity. So once we select the mesh, we can then pick our node selection method, either picking them singularly, a box select for surface available nodes, or a box volume and lasso volume to select certain nodes throughout the volume. So if I select a box volume, I can just draw a box and it'll select all the nodes within that region. Once I'm happy with that, I can then select on our results and then apply those nodes specifically to this. So with those nodes highlighted, you can evaluate this just like a normal results. And what it does is it identifies the nodes that you've selected and essentially builds surfaces with those results quantities so you can visualize that. And with that, you can see, you can kind of zoom in on this local region where I selected. I've highlighted only these certain nodes to extract those results. What's also handy, that's available accessing nodal stresses for post-processing. What's also available is another neat feature. I'll come back to utilizing name selections for that, but sometimes we may need to look and chart up combinations of multiple results quantities through our outline tree. One thing I wanted to show you next is the availability to generate charts and tables. So within Solution, we have various results quantities. We can literally highlight these results quantities we want to combine in a chart and select, for example, maximum principal stress on the block from a couple different load cases, and then we may want to also plot that against bolt pretension. So once we've selected those, we can then, with all these three highlighted, if we select Insert a Chart, this will create a chart item in the bottom of our outline tree with all the items we've selected. And you can always change this. You can add and subtract to that. You'll see down below, let me expand this a little bit. You can see our chart here, identifying all the quantities, the results with time. You have control on the axes and the output quantities. What's nice here is you can also choose to only display certain quantities from the items you select in terms of min and max. And so if I just wanted to display the maximum, I can go down to the details pane and omit certain quantities in our results. Let's get rid of all the mins, and now I have a little bit more concise data to show here. And you can turn on the legends just to identify these a little bit nicer. Also, what is nice with the tabular data, you can review the numeric quantities, but you can always copy this item and shoot this data over to Excel, for example, if you wanted to do some continuous post-processing in Excel. And that's a nice way to just shoot the data over there if you need it. That's chart data, so that's a handy way to utilize post-processing information. I'd like to open another poll here. And this particular poll is another query just to kind of see what you're interested in. With this particular poll, we're going to ask you what type of FE analysis do you typically perform, and what type of post-processing for the various analysis types. We have linear, nonlinear, static, structural, which we're showing you today. Perhaps you're running linear dynamics or transient dynamics. Maybe you need to do mostly heat transfer or explicit, highly nonlinear, short duration type of analysis. Do you need to run the stress analysis for fatigue or durability, or maybe some combinations? Okay, as you can see, many folks are doing linear, nonlinear, static, structural, or combinations of all the above. So they may be including some heat transfer in their static structural, maybe doing some dynamics. Okay, I've got one more item I wanted to show you in advanced post-processing, and this is getting a little bit more sophisticated in terms of accessing node and element data as well as using mechanical APDL commands. Perhaps you may have some routines to do some post-processing in mechanical APDL. Perhaps you have some custom calculations or some routine with APDL commands you want to include. I've got an example here to utilize that, and there's some key features I wanted to show with this. In terms of name selection, name selections, as you may know, let me turn off our mesh here. Name selections transfer over to mechanical APDL. If it's a body, it transfers over as a nodal component. If it's a surface, it's an element component. With a body, with a critical block here as selected to a scope to a body, this is a name selection that gets transferred as element components. Well, we can actually utilize a selection criteria with name selections to hone in on a local area that you may want to post-process. For example, I've identified critical block nodes, and you can define the scoping of your name selections, typically through geometry, but also what we call through worksheet mode. This worksheet essentially uses somewhat like select logic to build up the name selection. In this case, we're adding the body for a name selection to this critical block nodes, and then I'm converting it to a mesh node. So you can actually create a name selection and utilize this through the outline tree of mesh nodes. And what I've done further here is identified local nodes, again as a worksheet mode, and kind of honed in on some local region with respect to a local cylindrical system around my hole. So I want to take all my mesh nodes within a half-inch radius of that. And we can see on the graphics to confirm all the nodes that I've selected. Well, we can utilize name selections here. And if we were to insert a results quantity, let's insert maximum principal, we can scope that instead of to a specific body, we can scope that to a name selection. Let's go ahead and pick the existing local nodes. Once we evaluate that, we can look at the results quantity just in this region. So that's handy for managing nodes. What I wanted to show you with respect to mechanical APDL is within solution, you can include a command block. So this command block will run ANSYS APDL commands immediately after the /post1. So it's solved. You can go into /post1 and edit and insert commands to run a little post-processing job. In this case, we added the command block after the solution was solved. And I've got some commands here. Let me copy and paste this from an example routine here. And with that, let me briefly describe. We're going to resume the analysis database, which includes the name selections. And I'm going to select my local nodes name selection. We know those are nodes. I'm going to try to sort to get the maximum stress on those nodes. And then I'm going to say, maybe I want to look at, or maybe I need the number of elements within 90% or greater of that maximum stress value. If I have some kind of post-processing routine that needs that number, I can get the number of elements count within 90%. Once you insert the command block, this will be, again, executed just after post 1. We can also show these particular parameters we can send out to mechanical by identifying the output search prefix to take the parameters calculated and send them to the mechanical tool within Workbench. So I'm going to use this as a filter called anything starting with MY. I'm going to filter out and send this back to Workbench. So once we solve that, it'll run a small post-processing job. We'll come back. You'll see that in the details pane of our command block, we now say my SEQ max is 10,460, but I've got over 1,000 nodes within that 90% of that maximum value. Okay, and then let's see with that. A couple key things with looking at this. If you want to look at the results from the small post-processing job, you can come to solution information and look at not the results from the actual job. You can also get the post output, the text output from your small little post-processing job that you ran after the analysis. So this is a neat tool to work with APDL commands and get them back into the mechanical. So if we wanted to use this as a parameter within some design of experiment study, we can send this. We take a look back to our Workbench project page. Those results parameters are now being sent to the project. We can then control those through a design of experiment. So that's a neat way to run some custom post-processing script and access that information in a design study.